Okay, so now we'll start with stoichiometry, which is the last unit of Chemistry 20. And the first lesson of this unit is dealing with net ionic reaction, and we will do a short intro to stoichiometry, which in other words is calculation. So the word stoichiometry means calculation. So we'll start with the net ionic reaction. Net ionic reactions or net ionic equation is a chemical reaction that includes only the reacting entities. So it includes only the reacting entities. What is reacting in the equation? Because we have some entities that are known as the spectator ions, which are present in both sides of the chemical reaction. So in order to write a net ionic reaction, and this is kind of a review from what we did in the previous unit, in order to write the net ionic reaction, what do we have to do as a very first step is we need to write the balanced chemical reaction. So in this example, when we have zinc reacting with copper sulfate, then as the balanced chemical reaction will be something like this. So zinc solid is reacting with copper sulfate, which is CuSO4 aqueous, and this being a singular replacement reaction, you do remember what you recall what a singular replacement reaction is. We'll have copper solid and zinc sulfate. Now, this particular reaction is a balanced one because we have the same number of entities in both sides. So one zinc, one copper, one sulfate, one sulfate. Now, what do? Is we write a total ionic equation, known as we are writing all aqueous compound as ions. So total ionic equation on this case will be something like this. Zinc solid plus copper 2 plus and sulfate 2 minus. And on the other side of the reaction, we will have copper solid plus zinc and sulfate in aqueous solution. And we know that this is aqueous solution because we can refer to the information that we have in our data booklet in terms of which one is soluble and which one is not. So now, as you see here, sulfate is in both sides of the equations of the reaction. So that means that we can kind of cancel out. And now, when we have the net ionic reaction, or equation is the same thing, we will cancel out those that are spectator ions. So the ions that are in both sides of the equation. This is what it is. So it is, in this example, SO4 2 minus in aqueous solution is a spectator ion because it is appeared on both sides of the equations. Okay, so now let's work on this example. Let's write a reaction, a total ionic reaction and a net ionic reaction for the reaction of silver nitrate with potassium chloride. So on this case, as always, when we are working with net ionic reaction, we'll start with a balanced chemical reaction. So what we have is silver nitrate. And if you refer to the solubility table of if you're of your data booklet, then you will notice that it is soluble, and potassium chloride, it's soluble as well. This is a double replacement reaction. So what we will have is KNO3, which again is soluble, and GCl that is not soluble. So this is the balanced equation. The total ionic reaction is a reaction in which everything that is aqueous is turned into ions. Total ionic reaction or equation, whatever you want. Okay, so now silver nitrate is aqueous, so will be silver with the charge plus NO3 K plus Cl minus in aqueous solution. And now we have here potassium nitrate that is aqueous solution as well, so will be K plus and NO3 minus. However, silver chloride is not aqueous solution, is a solid one, so will stay as silver chloride. And what do we do after this? We, as a third step here, and this will be the net ionic reaction. We cancel what it is on both sides of the equation. So in this case, what we will have as both same in both sides of the equation is nitrate and potassium. Those two that I just canceled out are known as spectator ions, and the net ionic reaction will be net ionic reaction will be silver ion plus chloride, and on the other side we will have silver chloride as a solid. And if we want to identify the spectator ions, so the spectator ions, in this case we have two, is the nitrate and potassium ion. Okay, so let's take a look now at the next one, when we have to write a net ionic equation for the reaction of potassium phosphate with calcium chlorate. So the reaction will be K3PO4 in aqueous solution, and this is based on the solubility table that you have in your data booklet. And then calcium chlorate, so CaClO3, and again is in aqueous solution. This is a double replacement reaction, so the products will be potassium chlorate, so will be KClO3, and is an aqueous solution plus calcium phosphate. So Ca3PO4. And based on the solubility table that you have, this is solid state. Now let's balance this. I will show you the balance right away so that you don't have to, but you can go through the process and balance. So this is the balanced chemical reaction. Now let's write a total ionic reaction. So we will have 6K plus in aqueous plus 2PO4, 3 minus in aqueous plus 3 calcium 2 plus 3 minus, and then we'll have 6K plus 6 ClO3 minus and calcium phosphate solid. So now what is common in both sides of the reaction? We have 6 potassium and then 6 chlorate. Everything else then is it's only in one side of the reaction, so that the final or the total net ionic reaction, not total, but net ionic reaction will be 2PO4 3 minus in aqueous solution plus 3 calcium 2 plus in aqueous solution will give us PO4 in solid state. Yeah, you can stop here the video and then work on the assignment that correspond to the net ionic reaction. Or you can continue with the video in stoichiometry and then finish the assignment as the video is done. So now we'll move to that intro to stoichiometry. And stoichiometry is actually quantitative analysis of a reaction. So it is pretty much calculations. And this is what actually means in ancient Greek, I think even now, but yeah. So the ratio between the molar coefficient of the, what we have to take into the consideration is the molar ratio, which is the coefficients in a balanced equation. This is determining how much product is produced in the reaction. Or how much reactant is required to produce whatever we are looking for. So the balance equation that we always start any work in stoich is showing the molar ratio. Now let's suppose that we have this reaction here. So boron is reacting with magnesium sulfate to produce magnesium boron and sulfur gas. And this is a balanced equation because we have 16 boron, 16 on the other side, 8 magnesium, 8 sulfur, 8 sulfur. Okay, so now what those numbers are in front of the compounds that we are dealing with, and when there is nothing is 1, are showing us the molar ratio. So in other words, what it's saying here is that it needs 8 moles or 8 molecules, 8 parts of boron gas to react in order to produce, let's say, 1, in this particular reaction, 1 molecule or 1 part of the sulfur gas. Now, when we are asking here, what is the ratio of magnesium sulfate, so this one here, and sulfur, so we see 8 and 1. Okay, so it is 8 to 1, or in other words, means that it needs 8 moles of magnesium sulfate to produce 1 mole of sulfur gas. And what is the ratio of magnesium boron and magnesium sulfate? So this and this. It is 8 moles of magnesium boron and 8 moles of magnesium sulfate. So now what we have here is 8 to 8, or in simplified one will be 1 to 1. For the purposes of calculations and what we are working on chemistry, we don't even need to simplify it. We just need to identify the molar ratio. Okay. Now, let's move now to a further understanding of the coefficients. So when we have the same reaction, that means that for every 8 molecules of boron that reacts, 8 formula units of magnesium sulfate will need to react. And for 8 moles of magnesium sulfate that react, 1 mole of sulfur is formed. For every molecule of sulfur gas formed, you need, so now Br2, so you will go here, you will need 8 molecules of boron. For every 2 formula units, of magnesium boron that is forming, form 2 molecules magnesium boron. So magnesium boron, 2 molecules of boron, because the ratio is 8 to 8. So what you do is 2 formula units of magnesium boron, 8 moles of Br2 over to, or 8 formula units of boron over 8 formula units of magnesium boron. So this and this is cancelled out, and then you will have 2 times 8 divided by 8, which is equal to 2 formula units. But the question would be, what if it is not that simple? Okay, so what if we don't have those numbers, nice numbers as 8 and 2 and 4 that round up perfectly? So on this case, let's say that we have 0.16 units of sulfur. How many units of bromine will be needed? Okay, so now what we will do is we will use the molar ratio, or what I did before. We have been doing this, we've been doing stoich without naming it that it's stoich even before. So now, let's see now what is happening here. So we have aluminum oxide that is decomposed in aluminum and in oxygen gas. So this is solid state. And then let's start with balancing it. 2, 4, and 3. What is the ratio of aluminum oxide to aluminum? So it is aluminum oxide to aluminum will be 2 to 4. 2 to 4. What is the ratio of the oxygen to aluminum oxide? So 3 moles of oxygen and aluminum oxide is 2 moles of aluminum oxide. You can say 3 to 2 or write it as you see it here. And what is the ratio of aluminum to oxygen? So aluminum to oxygen. Well, let's say that it is 3 moles of aluminum is, 4 moles of aluminum, not 3. 4 moles of aluminum is 3 moles of oxygen. So you can say 4 to 3. Now let's fill this table out using the molar ratios. Okay, so now what we have is oxygen has 0.75 moles. Okay, so now what we are looking for is the moles of aluminum. So we'll start like this. Always with what is given, 0.75 moles of oxygen times, now the molar ratio between aluminum and oxygen is 3 to 4. So 3 moles of oxygen are needed or are produced when 4 moles of aluminum is produced. So moles of oxygen and moles of oxygen is cancelled out. And then what we have here is 0.75 times 4 divided by 3. And the answer will be in moles of aluminum. So when you multiply those together, then you will have, you will have 1. And when you are looking for the moles of aluminum oxide, then what you will do is you will use the moles of what is given, 0.75 moles of oxygen times. You will look now for the ratio, molar ratio between oxygen and aluminum oxide, which is 3 to 2. Now, 2 moles of aluminum oxide are needed to produce 3 moles of oxygen, or when 3 moles of oxygen are produced, 2 moles of aluminum oxide are used. So then the ratio is 3 to 2 or 2 to 3. So it's like 3 moles of oxygen, 2 moles of aluminum oxide, or 2 moles of aluminum oxide, 3 moles of oxygen. So this is what we are doing, is we are multiplying by a ratio of 1, because it is it is the same thing that is produced in both sides. But we will choose the ratio 1 or 2 based on the fact what are we using to cancel the moles of oxygen. So then that means that we will use a ratio 2. 2 moles of aluminum oxide are used to produce 3 moles of oxygen. So moles of oxygen is cancelled out, and then we will have 0.75 times 2 divided by 3 is equal to 0.5 moles of aluminum oxide. And this is how we will complete all this table. I will stop here, and I suggest you to stop here, and then I will show you the completed table, and you can check with your work. So this should be the table completed. You can, using the logic that we explained here, you can check your work with the numbers that you have here or the key that you have here. Now, excess reactants are the reactants that are still present even when the reaction is completed. So there are reactants that are still present after the reaction is completed. And a limiting reactant are a reactant that is consumed, is used up after completing the reaction is completed. This is what the lesson 1 is about, and I will suggest you to work on the assignment on lesson 1. It starts with the net ionic reaction and some balancing here, then works on some of the introduction to stoich.